Alright, welcome to AP Physics 1 Unit 1 Ultimate Guide. Basically, this is just going to be a compilation of all of Unit 1 for AP Physics. These are the 5 subunits that AP has it broken out with a little fun picture that I drew all by myself. Um, so yeah, feel free to jump around. I'll have all the timestamps in the description. Some of them are broken up into a couple sections, like 1.3 has a few different ones. So yeah, so feel free to jump to what you need to watch or watch hours of physics videos because that sounds like a lot of fun. So yeah, hope you enjoy. So yeah, let's talk about scalars versus a vector. What is a scalar? What is a vector? Um, what does that mean when you say scalars? Because we'll be using scalars and vectors throughout the whole class, so it's kind of important fundamental information here. So yeah, let's talk about what are some examples of scalars that we might see, and what is their like kind of vector form. So like an example of a scalar that you all are probably very familiar with is something like distance, for example. And a vector form of distance would be called displacement. So what is the difference between a distance and a displacement? We'll talk a little bit more about this in the next video. Um, But as you see there, the scalar quantity is only the magnitude, while the vector has a magnitude and a direction. So if we travel from point A to point B, and we're going down like this, right? Um, this scalar quantity might be, let's say, 5 miles. So the scalar would be, the distance would be 5 miles, but the displacement would be like 5 miles south, let's say. So it needs this distance part, which that's what makes it a vector is the distance. And another thing that we'll talk a little bit more about, but for a vector, at least for displacement and distance, if you were to travel along path 2, let's say, your distance would be greater than 5 miles because you're traveling a longer distance, but your displacement is still just your final position compared with your initial position. So it would still be 5 miles, your displacement, but your distance can be different. So that's like the distinction there. So another example of a scalar would be like speed, how fast something is moving, while the vector would be like velocity. So if someone is traveling, let's say they're coming down here at 60 miles per hour, their speed is 60 miles per hour, but their velocity has this 60 miles per hour south. And something that could be different is like you have individual speeds along each point in your path, but you could also have individual velocity, but your velocity direction is going to change here. So when we talk about velocity, we'll often talk about the average velocity over the period, so that you don't have to account for each one of those. But the main thing here is that every vector needs a direction associated with it. So just a few other scalars that we'll commonly see is stuff like mass or time or energy units are all scalar quantities. They don't have a direction. Some of these can't have a vector version because a mass does not have a direction. It's just how heavy, kind of. Not heavy really, but you know what I'm saying. Um, so then like other vectors we'll talk about is acceleration. Oops. Acceleration or force or momentum. And we'll talk more about these throughout the different units. But these are stuff we'll see throughout the class and throughout your time in physics. So it's important to know what's a vector, what's a scalar, and the differences between them. All right, so let's talk about how do we notate a vector. So a vector is always denoted by an arrow. So if I just draw an arrow, let's say like this, that is going to be a vector. So a vector will have its magnitude, which is the length of it. I'll just abbreviate that. That's the magnitude, and it also has the direction, which is the direction it's pointing. So if it's off some horizontal, you could have some angle of the vector, which then, now there's two different components of the vector that'll have like your x component and your y component of the vector. And we'll get more into specifics when we need to use these, but it's important to know that there is some direction in one coordinate and one in the y direction. So that's how the direction is displayed. And so we usually call this end the tail of the vector, and this end with the arrow the head of the vector. Sometimes call it other things, but that's how I'll notate it. So when we're comparing vectors, it's important to know like the magnitudes of the arrows can be displayed as relative to each other. So like if you wanted to say like 10 meters per second right, you would draw, let's say, a vector like this, right? So now this distance is 10 meters per second, but if I wanted to draw like 20 meters per second to the right, I would have to draw this arrow like twice as long to show that the magnitude is twice as long as the original one. Or if I wanted to show 10 meters per second left, I could then draw it like this and have it like that. So that's how arrows are important, because the direction matters and the lengths are for their relative magnitudes. And the last little bit of vector notation is for variables. So if we want to have a vector variable, let's say we're doing like velocity, vectors will typically be shown with a little arrow above it. Or sometimes if you're only talking about one direction, you can say have the direction here. So like this arrow right here, if this was vector v, this would be v of x and this would be v of y, right? So it's already kind of showing the direction within it, so it doesn't need the arrow at the top. While a scalar, like let's say mass, would just be an m, no notation at the top. So if we were to write like a common equation, we might see like force equals mass times acceleration, right? You've probably heard about that. The force will have a vector, the acceleration will have a vector, but the mass is not a vector because it's a scalar. Alright, so let's do some adding vectors here in one dimension. We'll do it using drawing, and then do it using like variables. So, alright, let's read the question. So we got a runner runs 3 miles due north, then runs 5 miles south, then runs another 8 miles north, and we have to draw the resultant vector. Alright. Alright, so we'll start down here. So we just have to choose some starting point to start our vectors at. So I'll start at this point right here. So we see the first thing that happens, the runner runs 3 miles north. So I'll use each line here as 1 mile to draw them relative to each other. So I'll have the arrow run up this way as 3 miles north. So I'll just note this as 3. And now it turns around and runs 5 miles south. So whenever you're adding vectors, you always want to draw them tip to tail, I think. So you can start from here and draw it down 5. So that would be your 5 miles south. And then it turns around again and runs another 8 miles north. So I can draw it from down here and go 5, 6, 7, 8. Okay, I don't know why it got so thick there, but whatever. So then we have 8 right there. Alright. So now we see that we could imagine these being all in one line, but just so you can see them, they're moved over. The vector is not actually moving to the right or left at all. So we have to draw a resultant vector. So that means we want to start at the same place as our original starting point and draw to the top here. So I'll use a different color. So our resultant vector is starting from this spot and goes up to the top here. And usually sometimes resultant vectors are drawn like with this double line here so that they stand out. And so now how many miles is this? So we don't even have to worry about all this other stuff that happened. We can just count like 1, 2, 3, 4, 5, 6. So our resultant vectors will be 6 miles. And because it's up and we denoted north as up, 6 miles north. Right? Alright, so let's try doing this one down here. So we're going to use the same question but do it using different variables, right? So I'll just scroll down. So we have, I kind of need the question actually. Alright. So we know that the runner runs 3 different segments per se. So we'll denote the positive direction, and I'll just write this up here, the positive direction as north, and the negative direction as south. So if we want to find our displacement first, which we'll just write as a big D. So we have 3 different displacements here. Right? So if we want to find the total displacement, we know that these will have directions, and as we noted over here, these signs of each variable will be how we get the direction. So first is 3 miles north. So we can draw in the 3 miles here, and it's a positive 3 because it's going up, it's going north. And then it goes 5 miles south, so we're still adding this variable here, but it's going to be going in the negative direction because it's south, so we can say -5. And then the last part is going another 8 miles north, so we can use a +8. And if we solve this out, you will see we get 6 miles, and because it's positive, it's going to be going north. And we see that's the same answer we got up here using the drawing. But now what if we want to find the distance? And I'll just write the distance as a small d equals d1 plus d2 plus d3. I'll scroll down a little bit. So if we want to find the distance, we know the distance is a scalar quantity, so we don't need any direction. So there's no positive, negative. We just want to write each mile distance they traveled. So they traveled 3 miles at first, and then they traveled another 5 miles, and then another 8 miles. And notice we don't care what direction it's traveling, it's still traveling that distance. So your final answer will be, if we add these up, 16 miles, and note there's no direction on this. So even though they traveled 6 miles north in the end, the full journey is 16 miles. Alright, displacement. So as we talked about a little bit in the last video, these are all vector quantities. So they will have a magnitude and a direction. But we'll go ahead and assign some formulas so we can do some calculations with these. So displacement, we'll draw this as a change in x, but really it could also be in the y direction, and that applies for all of these. So the change in x is equal to the final position minus the initial position. So again, kind of what we talked about, if you're going from one spot to another, it doesn't depend on the path you travel, it only depends on this the final position subtracted from the initial position, and we'll do some calculations with that. So for average velocity, we can write as v average. And I guess if this is a vector, it should also have a little arrow on it, is the change in distance, or the displacement, over the change in time. And this time is a scalar quantity, obviously, because it's time. And then we have our average acceleration, which is the change in the velocity over the change in time. So however long it takes to get from one point to another is the average velocity, and it only depends on this final and initial, and how much the velocity changes over this time is how much acceleration there will be on average. And just because the average velocity might be like 10 meters per second does not mean you're going 10 meters per second at every point. It just means over the course of time, that was your average speed, or average velocity, we'll say. So cool. Okay, let's do an example with this. We have Bob traveling 550 kilometers south in a straight line is what that should say for a football game. I'll just fix this real quick. He travels for 200 kilometers in this amount of time. Then he takes a break for half an hour and travels the rest of the way in 3 hours. After the 3 hour football game, he travels this much north for 1 hour. What is Bob's average velocity? Okay, so we're given a lot of information here. So I'd always recommend to do two things before you start solving, and that's list what variables you have and draw a picture, if it's applicable. And you'll pretty much see me do this for all physics problems, because you're given all this information, you don't want to jump in and start writing stuff down. So first I'll just draw a picture of what is actually happening here, right? So we know Bob is traveling this amount south, and we're looking for the velocity. So we can just start, we'll make the start point right here, and it's traveling 550 kilometers south. So I'll just draw a line down here, and I'll say this is 550 kilometers, and we'll make down south. So if I do a little compass here, north, south. Okay, we only really care about north and south for this question. And then so over the course of this travel, he starts by traveling, and I'll make this another color so we can see this is the overall. So he starts by traveling 200 kilometers in that amount of time. So we'll just draw an arrow. Okay, so that's 200 kilometers in 1.75 hours. Okay, and then he just stops for 0.5 hours, and then he travels the rest of the way, and that is done in 3 hours, right? Okay, and then the football game is 3 hours long, and then he travels up 150 kilometers in 1 hour. So cool. So this is our picture. We kind of get a better idea of what's actually happening. So let's go ahead and list out some variables. What variables do we have? Well, actually, for this equation, since we already know what we want to find, and we just wrote down the average velocity, we know we want to find that. So let's write our equation that we're going to use. So V average is equal to the displacement over the change in time, right? So first we need to find the displacement. That's the first thing we need to find. And so we know that the change in displacement is the final position minus the initial position over, and then we can leave it over time. And a lot of times for a change in time, I'll just denote as a t because we're assuming the starting time is time 0. But sometimes if you're finding a time within something, you'll use final minus initial there as well. Okay, so let's list out what do we have here. So we want to find our V average, we know that. So V average is what we want to find. So we can denote our starting position, x initial, and this 0 just means initial, or it's usually called not. So that'll be our initial position, and we can just choose really anything, right? Because we're not given no coordinates here. So we'll just, to make our lives easier, we'll just make the initial position 0, or 0 kilometers. So now we need we know we need our x final. So do we have our x final, right? And we do have our x final, because we know that he travels 550 south first, and then he comes back up another 150. So his final position will be minus 550 if we denote south as negative, as we typically will, plus the 150, and that'll all be kilometers. So that's the final position because he starts at 0 here, comes down a whole 550, and then goes up 150 right there. Okay. So yeah, if we solve that out, we'll get a negative 400 kilometers. And what this negative means is basically south. But we'll keep it as negative for now, so that when we solve in our equation, that negative will take care of the direction. All right. And then we have time, right? So over time. So how long did this trip take? So for this, we'll simply just add up each time. So we can add up the 1.75 plus 0.5 plus 3 plus 3 plus 1. And if we add this up, the time will equal 9.25 hours. And I'm really just pulling these times right here for all of these and just adding up. That's the total time of this trip. Alright, so now if we look, we have all these variables. We can simply solve for V average here. So now that we have the equation and we're already set to solve it for V average, I can go ahead and plug our variables. So we know V final is a negative 400 minus the initial, which is just 0, over our time, which is 9.25. And I should put units here. This is kilometers, right? So if we go ahead and solve this out, we will get a negative 43.24 kilometers per hour. Cool. So what does this negative mean? He's not traveling at negative speed. This is showing the direction. So if we were going to write our final answer, we should really write it as our V average is equal to 43.24 kilometers per hour. We can say due south, or due S. Sometimes we'll abbreviate it as S. And that right there is our final answer. All right. Cool. So that gives us our final answer. And so we were given all this stuff. And see, we didn't even need the distance between here and here. We just need this final and initial and the time, and we could find our V average. All right, so let's do one more here. So we have a ball is rolling up a hill for 0.75 seconds. Its average acceleration is 4 meters per second squared due west. Its final velocity after that time is 15 meters per second. What is the ball's initial velocity? All right, so again, we have all this information. It might seem overwhelming. Let's start by drawing a picture. And first, I'll just make a little compass so we can denote our directions: north, south, west, east. Okay. So we'll denote west as negative, south as negative, east as positive, and north as positive. And I'll keep these conventions throughout. It's pretty typical. So we know a ball is traveling east, right? So I'll just draw a picture here. We have a ball, and it's rolling up a hill that direction. Its final velocity is this. So we just know the final velocity, right? So the ball is traveling, and its final velocity is east here in this direction. We'll just imagine like there's like a little hill here, right? The VF is right there. And so we know the acceleration is west, so the acceleration on this ball is in that direction. They're in opposite directions. And we need to know the final velocity. Alright, so let's go ahead and list out what variables are we given. Let me make this a little bit thicker, I think. So we know we're given the time. So the time that this is going on for is 0.75 seconds. We know the average acceleration is 4 meters per second squared. And this is due west, so we'll give this a negative 4 meters per second squared. And we also know the final velocity. And we'll just write as VF, and that is 15 meters per second. And that's east, so we'll say positive. Alright, and we want to find what is the initial velocity. And so really we don't know the direction here, but if the final velocity is this direction and the acceleration is moving the opposite direction, it probably has to be in this direction. I don't know why that arrow got weird. Anyways, it probably has to be in this direction, otherwise the ball would be going in this direction at the end, which it's not. Okay. So let's write out our equation that we were given. So we have the average acceleration is equal to the change in velocity over time, which equals the velocity final minus the velocity initial over time. So we have all the variables except for this one, which is what we're looking for. So what I always recommend doing is rearrange the equation first and then plug numbers in. So we can multiply the t to the other side to get the average acceleration times time equals the v final minus v initial. And we want to solve for this variable, so we can add it to here and subtract the acceleration time to get v initial is equal to v final minus average acceleration times time. And really all these are vectors as well. So now that we've got this in this format, we can now plug in the numbers. So we want to solve for v initial. We know the final velocity is 15 meters per second, minus the acceleration is in the negative direction because we're calling it the west. So it'd be negative 4 meters per second squared. And the time is 0.75 seconds. So this seconds will cancel with that one. We'll get meters per second. So that the velocity initial is equal to 18 meters per second. And because it's positive, that means it's going to be east. And yeah, that's be the final answer. Alright, cool. So that'll be the final answer there. So now we know what the initial velocity was. The initial velocity was 18. And notice here that it starts off at 18 and ends at 15, which means the acceleration must be in the opposite direction because it's slowing the ball down. And that's why I kind of drew it on a hill here, because you can think of if it's going up a hill, the ball is going to start slowing down because the acceleration is in the opposite direction. This isn't the best example to actually think about because the acceleration is really down, but there will be that horizontal acceleration here in the opposite direction. So that's why the velocity is greater at the start than the end. So you always want to think about it, does your answer make sense? To make sure you didn't make any mistakes, you didn't forget any negative signs, stuff like that. So these are the three big kinematic equations that you'll see in physics. So a few things about these. The first thing is they only apply for constant acceleration, which means the acceleration must be constant. It cannot be changing, otherwise these will not be able to be used. Another thing is that these equations are all given in the x direction right now, but they can also just be applied in the y direction. For example, this equation could be the y position final minus y initial plus the velocity initial in the y direction times time plus 1/2 the acceleration in the y direction, t squared. And something to note about the y direction is that the acceleration is going to be the acceleration due to gravity, because when if you're just in free fall, the acceleration is usually going to be the acceleration due to gravity. So we denote it as a g, which equals 9.8 meters per second squared on Earth. So if you're not given acceleration and something's in free motion in the air, the y acceleration is going to be this gravity here. Alright, so let's do a couple examples using these equations. Alright, so we have Bob is traveling at 60 meters per second due west and starts accelerating at 15 meters per second squared due west for 10 meters. What is Bob's final velocity and how long is he traveling for? Alright, so first thing I always recommend is start by listing out what we're given here. So we know he initially is traveling at 60 meters per second due west, so that's the velocity initial is 60 meters per second. And we know it's due west, so if we have our compass over here, we'll just draw it over here. Typically we'll use west as the negative since it's to the left. So we'll denote west as negative, and I'll just draw that over here. So we'll make this value a negative, and now from now on any west directions will be negative and east will be positive. We also know that he starts accelerating at 15 meters second squared due west for 10 meters. So his acceleration is equal to 15 meters per second squared. And since that's also due west, we'll have in the negative direction. And then finally we're given that it's for 10 meters. So we know that the change, and we'll just use x here, is going to be 10 meters. But since he was traveling west, that change is also going to be west. So if we draw out, let's say, we'll just draw a quick picture here. We have Bob right here, and he's traveling 60 meters per second. This change in x that he travels is also going to be in that direction. So we will also have to use a negative sign here to denote that. And so we want to know what is the final velocity and what is the time, how long was he traveling for. Alright, so this is what we're given. What equations can we use to start solving this? So first off, I see that if we look back at the equations that we need to find the final velocity, right? So if we try to use this equation has time here, and we don't know time yet. And this one also has time, we're not given time, but this equation right here is not given time, and we can solve for final velocity. So that's probably going to be the one we want to use here for this first part. So we can write this out as velocity final squared equals velocity initial squared plus 2 acceleration, and it's written as x final minus x initial. But we know that this is just equal to the change in x, right? So this we already have this variable, and we have all these other variables. All these variables we all have, so we just need to solve for this velocity final right there. So if we take the square root of each side, we end up getting that the v final is equal to the square root of v naught squared plus 2a delta x. And this could also be a plus or minus here. Okay. So now that we have our variable we want on its own, we can go ahead and plug in values here. So the velocity final is equal to plus or minus the square root of the initial velocity, which is a negative 60 squared plus 2, the acceleration, which is negative 15, and the change in x, which is negative 10. And we go ahead and plug this in, and we will get a velocity final that is equal to 62.4 meters per second. And we see we have this plus or minus here, right? We have this plus or minus, but we don't know is this plus or minus, right? So we have to think back to what makes sense, right? What would make sense? Bob is traveling west. The acceleration is also west, so he's speeding up. It wouldn't make sense for the direction to be in the east, right? If he's traveling this way and then getting faster, his final velocity is also going to be in that direction, so we would use a negative sign to denote this. But when writing our final answer, we can drop the negative sign and just write due west. And that will give you your answer for the first part. Okay, but now we need to know how long was Bob traveling for. Well, now if we look back at our initial equations, now that we have this v final, we could use this first equation. We could also use the second equation. But if we were to use the second equation, we would have to use quadratic formula since we have these t squareds here. So this first equation will be much easier to use. So we can use this first equation of Vf is equal to V naught plus AT, and we want to solve for t. So we can subtract this, so Vf minus V naught equals AT, and if I just solve for t now, t is equal to Vf minus V naught over acceleration. So I'll scroll down a little bit. So now that we have this with the t separated out, we can plug in our values here. So the final velocity is a negative value as we determined before. That's why we need to determine it. And our initial is also a negative value, which is negative 60. And we divide this by a negative acceleration of negative 15. And that will give us 0.163 seconds. So that's how long he was traveling for. So that's why it's important to keep track of your signs here, because if you mix up your signs, you will end up getting a different value. But if you were to choose positive for everything and make West positive, you would still get all the same answers. So if you wanted to try that on your own, you could do that. Alright, let's do one more example here. So we see Bob is on a 120 meter tall cliff and throws a ball straight up at 12 meters per second. What is the final velocity of the ball just before it reaches the ground? Alright. So again, let's start out by listing what variables are we given. So we know the initial velocity, v naught, is equal to 12 meters per second. And since he's throwing the ball upwards, we're going to leave this as a positive 12 meters per second. And we'll know up as positive and down as negative. Okay? We know that the cliff is 120 meters tall. So to make this a little clearer, I'm going to start by drawing my picture actually. So let's say we have a little cliff here that is 120 meters, right? The ball starts here and is thrown up at 12 meters per second, and it goes up, and then it comes all the way back down, and right before it hits the ground, it has some velocity final, and that's what we're trying to find, right? So when we want to know what is this 120 meter cliff, right, we can actually set the change in y equal to the 120 meters. And because it's starting at the 120 and ending at the very bottom, this will be a negative 120 because it's going down 120 meters. And notice that we don't care how high the ball gets when it's thrown up. We only care about this initial position and final position of the ball. So it's important that we don't care how high the ball goes because it's going to be thrown up higher than 120 before it falls. But we only care about the initial and final. Okay. So yeah, and we want to find the velocity final. That's what we're looking for. Now there's one more piece of information that we're not told, but we do have, and it's because we can assume we're on Earth here. So there will be an acceleration due to gravity in this y direction that's equal to a negative 9.8 meters per second squared. And gravity will always be negative because gravity is always going towards the Earth. Okay. So now I have to decide what equation do we want to use here. And again, if we look at them, we're looking for this velocity final, but we don't have time. We're going to use that same equation we used in the last problem. That is the v final squared equals the v initial squared plus, and then this time because it's in the y, we can say 2g delta y, because this is the change in x. This is acceleration. And we have all these variables now. We have enough information to solve it. So we can now go vf squared is, or not vf squared, but just vf is equal to the square root of v naught squared plus 2g delta y. And now that we have all of these variables, we can go ahead and plug them in. So vf is equal to the square root of v naught, which this is going in the positive direction. So it's 12 meters per second squared plus 2 and negative 9.8, and the change in y, which is 120. And this will also have a plus or minus on it, so the v final will be equal to 50 meters per second, right? And now we have to decide, is this a negative or positive? Well, when we draw our picture, the ball is going up, and then when it's coming down right before it's the ground, it's falling down towards the ground, so it'll be a negative right here, which means that our final answer will be 50 meters per second down, and that'll be our final answer. So always make sure you have the direction when you're solving for a vector value. This is super important and can be really tricky when you're first starting off reading these graphs. So this will go over how to read and convert between position, velocity, and acceleration versus time graphs. And I'll kind of just be explaining them as we go here. So let's just jump into the first question. We have a position versus time of Bob traveling is shown down here. And we're going to denote the x position with north as positive and south as negative. So we have this position versus time graph here. So this is the position that they're at, and this is the time. And we'll just assume here that this is each square is like 1 unit in meters, and then these time stamps are shown on the bottom. Alright, so the first thing it asks is, when is Bob traveling north and when is he traveling south? So basically we want to know, when is Bob going north and when is he going south, right? So let me just scroll down here a little bit. Alright, so we'll write our north values here and our south values. Okay, so how can we tell when is Bob traveling north and when is he traveling south, right? So we denoted north as positive and south as negative. So when is Bob traveling towards the positive direction? So if we think about what are we looking at here, this is a position graph. So let's just take this first segment here from time 0 to time 5. We see at the initial point, the position is that x equals 0, and at the final point, x equals 2, which means during this interval, Bob is traveling towards the positive direction. So that means during this first interval from 0 seconds to 5 seconds, Bob is traveling north. Alright, now let's look at this next chunk from 5 to 9. We see that at 5 he's at position 2, and at 9 he's at x position 2 as well. And during this whole time, his position is constant, so he's not traveling north or south here. Alright, so let's take our next one here. We have from 9 to 13. At point 13, he's now at x position equals 4. So he's going from 2 to 4. The position goes from 2 to 4, which is getting more positive, which means that will also be traveling north. From time equals 9 seconds to 13 seconds. Alright, so now at 16 seconds, he's now all the way down here at x equals negative 2, or negative 3. So since he's going from a large value to a small value, he's going to be traveling south, so that 13 seconds, from 13 seconds to the 16 seconds. Okay, and then at 20 he's at 0 again, which means he's again traveling north from 16 seconds to 20 seconds, and then from 20 to 25 he ends at x equals 4 again, so he's also traveling north from 20 to 25. So if we notice here that for the values, we can also look at the slope. So this slope is a positive slope, and we will soon find that the slope is the velocity. So the slope of the position is the velocity. So we know that the velocity here is positive, the velocity is positive, the velocity is negative, oops, the velocity is negative, the velocity is positive, and the velocity is positive. So that will also tell you what direction you're traveling. When the velocity is positive, it's going towards the positive direction, which in this case is north. So the next question asks, what is Bob's displacement and velocity during the time interval from 0 to 5? So displacement we pretty much already solved for, because we know that the x initial is equal to 0 and the x final is equal to 2. So the change in x is equal to x final minus x initial, so that the change in x is equal to 2 minus 0, which equals 2 meters. That'll be the displacement. But how do we find the velocity? So we know that the velocity is a slope, but we can also go to our average velocity equation, which is the change in x over time, which we just found that it was 2. The time is from 0 to 5, which is 5 seconds. So the slope, or the velocity, will be, and this is in meters, and this is in seconds, so it'll be 0.4 meters per second. And that is the slope value of the line, but also given by this equation that we've learned about in the past. Alright, so now it's asking, when is Bob accelerating? So if we look at most of these lines here, this slope is constant on all these parts, which means there's no acceleration. But this portion right here, the slope is changing. Right? If I go, we can see here that down here the slope is like this, and then it goes like this, and it gets steeper, which means there must be some acceleration during this portion. But everywhere else, the slope is constant along all these lines, right? Doesn't matter, the slope is constant. So during this time interval, and this time interval only, there will be some acceleration. And we can't calculate the numerical value just from this graph, but we just know that there is some positive acceleration because the velocity is increasing. So from point time 20 to time 25, we'll have some acceleration. So from 20 seconds to 25 seconds. So we want to know, okay, another question. So what is Bob's velocity at time equals 10 seconds? So let's look back here. So at 10 seconds is right around here. What is the velocity? Well, we can't, it's hard to just find what is the velocity at this exact point, right? Because we need to find like initial and final position. But since we know the velocity is the same throughout this whole interval, we can use these points to find what the velocity is. So we know that the x is 4 from 2, and the point is from 9 to 13. So if we go down and solve for that average velocity, we know that the velocity will equal the change in x over the time, or the change in time in this case. That's why we'll have that change in time. It goes from 4, the x final is 4 minus 2, and it's 13 seconds as the t final, and 9 seconds. So that'll give us 2 over 4, which is equal to 0.5 meters per second. So, and this will also be north, and I should denote this is also to the north because it's positive for both of these. And so notice that if we find the slope of this line right here, we'll have the velocity over this entire time range. So that'll be true at this point 10 and anywhere else on the line. Alright, and finally, when is Bob's speed the greatest and when is it the least? Alright, so this kind of has a lot to it. How are we going to determine when the speed is the greatest and when the speed is the least? Well, if we scroll up here, we know that we can find the speed of each of these segments pretty easily. We already determined that it's the velocity, right? And since speed is just the magnitude of the velocity, we don't care what the direction is, we just care about the value. So we can just go through each one of these and find where is the speed the greatest and where the speed is the least. Alright. So from 0 to 5, we already determined that the velocity, I'll do all these in this green color. So for this first point, we have velocity equals the change in distance, which is 2, over the time, which is 5. So that'll be about 0.4. Now this point here, the velocity is equal to the change in distance, which is 2 minus 2 over this 4 seconds, but that's 0 because the slope is flat. So this will have 0 meters per second. So since speed is just the magnitude, you can't have any less than 0. So we know this point will be the least. But let's just keep going through these. So this velocity here will be from 4 minus 2, which is 2, over this time range, which is 4. So that would be 0.5. Now this time range right here, we have a velocity which is equal to the change in x. So this is the final point at negative 3, and the initial point is at 4. So we'll have negative 3 minus 4 over 16 minus 13, which is just 3. And that'll be negative 7 over 3. And since we're trying to find the speed, this is meters per second, we can just say 7 over 3 meters per second. So that's the largest so far. If we go down and check this one, we have the velocity equaling to 2 minus the negative 3, which is 3 over 4. And then I'm just gonna disclude this part. We'll say we're only trying to find up to point 20 because we can't find every exact velocity point here. So for right now, we will just say up to the 20-second mark, what is the greatest and what's the least. So if we look at all these velocities we found, this one is the greatest, since it is 7/3, which is larger than the other ones. And since we're just looking at speed, this one will be the least. Alright, so I could write that then, but I think that's good. Alright, so let's look at the next one. So let's look at sketching some graphs here. So we're given this position versus time graph, and we need to sketch the velocity and the acceleration versus time graphs. Alright, so we know that the velocity is the slope of the position, right? So let's try to sketch out this graph here. So let's just take it segment by segment. So we already found these slopes in the previous equation. So we know that this one was, what was this one actually? This one was 0.4 meters per second. So we know that's the velocity already because we already found what the slope was. So since it's constant throughout this entire interval, we can just draw a straight line, and this is noted as 1, so it'll probably be somewhere around here, as like right here. So this will be a constant line right here at 0.4. Alright, and then this one, since this slope is 0 from these 2 points, the velocity will be equal to 0. So this one will just be a straight line down here, which will be like that. And we can just continue doing the same thing for this one. So this one we already found was 2/4, so that's 1/2. So we can draw the velocity 1/2 right here, that's constant. Alright, now this one right here, we found that this one was, what, 7/3? So 7/3, so that's a little more than 2. But since it's now, this one is actually a negative 7/3. It's going down. So when we're drawing it on the velocity graph, we'll have to draw it below this x-axis because we're assuming the positive is in the same positive direction. So this one will be about 1, 2.5 or so, right down here. And this should be straight lines with no slope, but it's hard to draw. And then this one right here, what did we find this one to be? This one was 3/4. The slope of this is 3/4. So from 16 to 13, the slope will be right around here. And then this one right here, so this has a changing velocity, as we kind of drew out in the last time. It starts off with the slopes being light, and then they increase as the graph goes on. So we're going to assume that this is constant acceleration here. And so when it starts, it looks like it starts out pretty much at 0. So we can start our line from 0 and increase the velocity as we're going. So when there's this slope here, we can start it at 0 and have it increasing like this until it gets to 25. And we'll say that is the velocity graph there. It starts at 0 and is increasing, which is showing some acceleration. So now if we want to sketch the acceleration graph, we just need to find the slopes of the velocity graph now. So at all these points here, at all these points, the slope, which is now equal to acceleration, is 0. And all these 0, and we already answered that in the last example, that all these points are 0. But this one does have an acceleration, which we can quickly solve for if we say that the acceleration is the change in velocity over time. It ends at, we'll say 2, and starts at 0. So it's 2/5 seconds. So that would be the acceleration. We weren't able to draw exactly what the graph will be just from the graph. We would need more information. But if we assume this is the correct velocity versus time graph, this would be the acceleration. So that means all the way up till 20, this whole graph will be at 0. And then at here, it will be at 2/5, which will be somewhere around here. And that'll be the acceleration versus time graph. Alright, one final thing is the velocity versus time graph and some questions with that. So this can be pretty tricky, I think, and it can take some getting used to understand how to read these graphs and like what are they actually showing. So let's go through some examples. So we see Bob's traveling, giving the velocity time graph shown above. Alright. So when is Bob traveling in the positive and negative direction? So this is the same kind of thing we did with the position graph, but now we're given a velocity versus time graph. Right? So when we were on the position versus time graph, we just need to find where the slope is positive, which is when the velocity was positive. So if we're trying to find when Bob is traveling to the positive direction, we can simply just find where is the velocity of positive versus negative. So this is when velocity is positive or negative. Alright, so I'll just denote positive here and we can write these in. So that means that during this whole first segment, this is all the positive area. It's all positive here. Right? So that means that from time 0 to time 11, Bob is traveling in the positive direction. Seconds. Okay? And then from 11 to 22 is all in the negative direction, because now the velocity is negative and the speed he's moving at is now in the negative direction. So from 11 seconds to 22 seconds. And then this final point, it switches back to going in the positive direction from 22 to 27. Alright. Okay, so now we need to find what is Bob's displacement from 0 to 9 seconds. So displacement, how are we supposed to find displacement using velocity? We know how to find acceleration, it's just a slope, but how do we go backwards? How do we go from velocity to displacement or position? And to do that, we have to find the area. So if we wanted to find the displacement from 0 to 9, we would find this area under the curve right here. So this area will equal the displacement. So let me set this up so we can see. Okay. So we basically just want to find, this area. So we can do a little bit of geometry here and find that the change in x is equal to 1/2. We'll just do these as separately as like a triangle and a square here. So 1/2 the base, which is 4, times the height, which if we denote each one of these as 1, that is also 4. And know that these are in, let me draw out the units actually, because I think this will help prove that the area is the displacement that the units work out. So the 4 is seconds times 4 meters per second, plus this square here, which is another 5 seconds times another 4 meters per second. So these seconds will cancel out and we'll just be left with meters. And if we plug all these into a calculator, we get 28 meters. And also note that this is a positive 28 meters because these values are all positive. And if you were to get negative, it would be in the negative direction, and that would be the displacement in the negative direction. Okay. Alright, so when is Bob slowing down? Alright, so where is he slowing down? So this is, I think, was most tricky for people, because it's not as easy to tell when is he slowing down, because it's not just negative, positive. You might think, oh, when it's negative, but here it's in the negative direction. It doesn't mean it's going down. So we want to look at when is the velocity, when is the speed decreasing. So if we look at this first point, the speed starts at 0 and ends at 4. That means he's speeding up. At this point, there's no change in the velocity, so the speed will just be remaining constant. But from this 9 to 11, he starts at 4 and ends at 0. So this speed is decreasing. But from 13, his speed is now back up to 4 in the negative direction. But that means that he's speeding up. So this is slowing, and this point is speeding up. But at this point here, the velocity is 0, so that when this is going here, it's also slowing down. And so you can think about it as like you have a car that's going in the negative direction, and or actually to make this work for this graph, for this point right here, the car is going in this positive direction, but it's slowing down. So it gets slower and slower until it stops, and then starts speeding back up in the opposite direction. So only this point from 9 to 11 and from 13 to 22 is it slowing down. And so for a rule of thumb, it'll be slowing down if it's going towards the x-axis. And if it's going from away the x-axis, then it's speeding up. So it's slowing down from 9 to 11 and from 13 to 22. So I'll just write that in. 9 seconds to 11 seconds, and 13 seconds to 22 seconds. Okay, and finally, what is the acceleration from 13 to 22? So we already know the acceleration is the slope of the velocity graph, so we can do the average acceleration equation of this right here, which we already found that the final velocity was 0 minus the initial velocity, which is a negative 4, over a time of 22 minus 13, and that will give us 4 over 9 meters per second squared. So that'll be that velocity for this point. So a motion map is basically just a object in motion that's shown using intervals of a certain time. So in this first example, we'll show what a motion map looks like for a constant velocity with 1 second intervals, for example. This time could be anything. So we'll start by just drawing like a little dot and an arrow. And so for a motion map of constant velocity, at each one of these points will be evenly spaced apart, with the arrow being of the same magnitude. And this arrow in this case will represent the velocity. Now sometimes when you're shown motion maps, the arrows will not be there and it just shows like a freeze frame of a picture. And in that case, you just use the distances apart from the dots to tell, to describe the motion. So in this example, we have a constant velocity because this distance in between each is constant, and the magnitude of this arrow, both showing kind of the same thing. So now let's look at a motion map for something with constant acceleration. So in this case, the acceleration, this means that acceleration is equal to 0, but in this case there is some constant acceleration. So we'll start the same with a dot and an arrow, but at each point the arrow will get slightly larger, showing the velocity, and the distance apart is going to be different. So the distance apart will be different as well, and the arrows will start getting longer, because if there's acceleration, then the velocity is going to be increasing. And so this is showing acceleration in this direction. Actually, this shows acceleration in the same direction because it's getting faster in this direction. But you could also show acceleration in the opposite direction if you started with a longer line and got shorter with each frame, and this would show acceleration in this direction. Alright, so let's do a couple examples here. So here we're given 4 different motion maps, and we're just given the dots, and it says a ball is shown starting at time equals 0, and at each interval, and at intervals of 1 second, rank the magnitudes of acceleration from each ball. So you can think of this as the ball is rolling. You can think of it as the velocity of the ball moving this way, and at each second a picture is taken of where the ball is what this is showing, right? So let's just think about what do we know about each one of these? Let's start at A. So it starts off with some velocity, and it's spaced out here. And the difference between these spaces, I'll use a different color. The difference between these spaces right here, we have this space, and then it gets this length, and then this length. And at each one of these, the distance is getting a greater distance apart. So the acceleration here will be in this direction, and there is some acceleration. But if we look at B, each one of these distances are the same, which means in this case the acceleration is equal to 0. Let's look at C. For C, each one of these distances are also the same. So this acceleration will also be 0 because the distance apart are the same. Now in this last example, this first distance is very large, and then it gets a bit smaller, and then it gets much smaller, and then it gets really small here at the end. So both of these have some acceleration. In this case, it's going to be in this direction. So we want to rank these from smallest to largest, so we know B and C both have accelerations of 0, and we're looking for the magnitude, so we don't really care about the direction. So we know B will be equal to C. But how do we know the difference between D and A? Well, we see that A slowly gets larger, but in D it starts really large and very quickly gets really small. So that's telling us that D has a larger acceleration, and that this acceleration arrow will be larger than A. So A will be smaller than D. And one other point out here, if we wanted to compare the velocities of B and C, because this distance is much smaller than this distance, the velocity of C would be greater than the velocity of B, and that also can be shown for the dots here. So you don't need the arrows to tell you that, because if you think about if you roll a ball slowly, if you take a bunch of pictures, the ball is going to be closer to each other for a slower moving ball than something that's moving a lot faster. So let's look at one final example here. So which of the following motion maps show an object in acceleration? So let's think back to just what is the definition of acceleration, right? We know acceleration is equal to the change in velocity over time. So there must be some change in velocity. This is like the most important aspect of acceleration. There has to be a change in velocity, which means either the magnitude or the direction has to change. So if we look at this first example here, we see that this magnitude of these velocity arrows, or the distance apart from each one of these arrows as well, is changing. So that means A will have some acceleration. Now let's look at B. These magnitudes are pretty much constant, but the direction is changing, which means B will also have some acceleration. And we'll learn in later units when we talk about circular motion that this acceleration is actually pointed towards the center as it's rotating this motion, but that's for later. And then C, we see that this magnitude is larger, and then it gets smaller and smaller, and then it gets larger again. So there must be some acceleration in this direction first, and then at this point switches to the acceleration being that direction. So C will also have acceleration. And then for D, these distances are staying constant, the distances between the arrows are constant. So that tells us that D does not have an acceleration. So we would not select D here. So when dealing with one moving object, usually we have a stationary observer. So one of the references is stationary, like if we're saying how long it takes a ball to get from one spot to another spot, usually that second spot is the stationary observer. But what if we have two moving objects? We then can define a velocity relative as the relative velocity from A to B is equal to the velocity of A minus the velocity of B. So let's see this with a few basic examples to understand what's going on here. So let's say we have object A and object B are both traveling 5 meters per second to the right. So if we were to use this equation, VAB is equal to VA minus VB, minus VB, sorry. If we plug in 5 meters per second, since they're both to the right, they'll both be positive in this case. VAB will equal 5 minus 5, which will be 0. And if we think about this conceptually, let's say you and your friend are like in a car, and you're both traveling at 5 meters per second. If you look out the window to your friend in the car, you don't see any velocity change between you guys. So that's what that relative velocity is showing, is that there's no change in that velocity between you. Now let's say object A travels 10 meters per second to the right and object B travels 4 meters per second to the right. Well, if we write our equation now, velocity A is 10 meters per second to the right, while velocity B is only 4 meters per second to the right. So this relative velocity from A's perspective, will be 6 meters per second. So if we draw this situation out, we have a car going 10 meters per second, and then another car that's also moving in the same direction but only 4 meters per second. From this car's perspective, you will be going at 6 meters per second. And so if you were just a stationary observer standing on the ground, you would say the car is moving at 10 meters per second, but if you're also moving 4 meters per second, now that car only looks to be moving 6 meters per second, and that's what that relative velocity shows there. Now this final example is if we have object A traveling to the right at 5 meters per second, object B travels to the left at 5 meters per second. So again, we'll write our equation out. And if object A moves at 5 meters per second to the right, we'll denote right as positive. And then we have to subtract the velocity of subtract velocity B. But in this case, since it's moving to the left, we'll define it as a negative velocity. So we'll have a minus 5 meters per second here. And so the velocity A to B is equal to 10 meters per second. And so that's like if we had a car going down this way at 5 meters per second and a car that's coming the other direction at 5 meters per second. When you guys cross, if you look out your window, when we're at some point where the two cars are now right next to each other, moving in opposite directions, if you look out your window and look at that car, it'll look the same as if a car was moving at 10 meters per second and you were stationary on looking at the car. Okay, so let's do one final example that's a little more challenging. So we have on a one-way road, two cars are traveling in the opposite direction. One is traveling at 15 meters per second, the other at 30 meters per second in the opposite direction. They're initially 50 meters apart. How long does it take for them to cross? Okay. So we have a little more information, so let's write out what we have. So we'll denote the first car as, we'll say, velocity A, and in this case is 15 meters per second. And then velocity B will be the other car going 30 meters per second. But notice that it's in the opposite direction to the first car. So we couldn't really make either of them negative, but since this says opposite direction, I'll make the 30 meters per second negative, because one of them has to be in the opposite direction, right? And they're initially a distance of 50 meters. So we want to know the time it takes for them to cross each other. So we know that the velocity, just general velocity, equals the distance over time. So we have a lot of this information, and we can multiply by t and divide by the velocity to get the distance over the velocity. But what velocity do we use? Because we have two different velocities here. Well, since we have a car traveling at some velocity, we'll say 15, and the other one traveling towards it at 30, we need to find this relative velocity, because this distance is going to shrink faster than either of those velocities alone, right? So we need to find our relative velocity. So we know our relative velocity is equal to the velocity of A minus the velocity of B. So if we have a as 15 minus a negative 30, we get this velocity AB equal to 45 meters per second. And now we can use that here as the relative velocity because that's the one we actually care about. And we have our distance from the question. So if we go ahead and plug our 50 meters in for distance and our 45 meters per second as our velocity, we will end up with a time of 1.11 seconds, and that will be our answer. So when you are given a vector that is in 2 dimensions, such as a vector like this, we can break up this vector into its x and y components. So there will be an x component like this, and a y component like that, and some angle here. So when we're drawing this vector, if we say this vector is vector v, we usually denote this x component as v sub x, and this component as v sub y. So how can we solve for v sub x, v sub y, given this vector and this angle? So to do this, it's really just using some basic trigonometry. So if we have a triangle here, a right triangle, and we have, we'll call this side B, A, and C, we know that if this is our angle, cosine of this angle is equal to the adjacent over hypotenuse, so it'll be B over C, and sine of this angle is equal to the opposite over hypotenuse, which is A over C. And tangent of this angle is equal to opposite over adjacent. So using this idea, we can solve for these vectors as if this was sides of a triangle. So vector v sub x will be equal to, so in this case, this is what v sub x is. So if we multiply this c to the other side to solve for b, we would get c, which is the hypotenuse, which is just the total vector v, times the cosine of theta. And similarly, if we wanted to find vector v sub y, we would have to multiply the total vector magnitude, in this case, times sine of theta. And these would be the magnitudes because we're taking the direction away from this vector and breaking it up into one-dimensional components. And then if we were given the components but wanted to find the angle, using this over here, we could say that the angle theta is equal to v sub y, or not v sub y. It would be equal to the inverse tangent, or arctan, of the opposite, which is v sub y, over v sub x. And then one last thing is, if we wanted to find v, the magnitude of v given these components, we can use the Pythagorean theorem just as a squared plus b squared equals c squared over here. We can find v squared equals vx squared plus vy squared. So if we wanted to solve for v, we could just take the square root of vx squared plus vy squared. So that's how we can break up a vector in 2D and get its one-dimensional components. And this will be useful when doing problems since we can only analyze vectors in one dimension. Alright, so let's do an example here. So we need to find what is the magnitude and direction of velocity if the velocity is 15 meters per second up and 20 meters per second to the right, and what is the angle with the ground. So if we go ahead and draw this out, we see that first the velocity is, well, we'll draw the horizontal component first, so it's 20 meters per second to the right. So we can draw this like this, and this will be 20 meters per second, and then it's 15 meters per second up. So this will be 15 meters per second. So this resultant vector going from the beginning of the first one to the tip of the last one is this velocity vector that we're trying to find. And so we need to find the magnitude and the direction. So as we derived in the formula, we know that v equals the square root of vx squared plus vy squared. And that just comes from Pythagorean theorem. So this equals the vx, and this equals the vy. So we can just plug in these values here and get v equals the square root of 20 squared plus 15 squared, so that our magnitude of v, and sometimes when we're writing magnitude of a vector, we will draw these bars on the outside, so that this magnitude will be 25 meters per second. And so if we wanted to give this a direction, we would need to know the angle, but we could also say like up and to the right. But since we're just finding the magnitude here, we don't really need this direction. But we also are asked to find the angle, so we're trying to find this angle with the ground. So again, using the formula before, we know that the theta will be the inverse tangent of Vy over Vx, and we're given both of those values, so we can go ahead and plug those in. So that'll be 15 over 20, and that'll equal 36.9 degrees. And that's 36.9 degrees above the ground in this case, or above the horizontal. Alright, so now let's talk about adding 2D vectors. So all of our vector addition we've done before has been in one dimension, where we had, say, like one vector going this way, and then we add it here, and then we add it here. But we always add starting from the tip of the last vector and going and drawing the vector off of that, off of the tip of the last vector. So we're going to use that same idea when adding 2D vectors. So let's just draw out a 2D vector example. So let's say we had a vector like this, or let me draw this better. Let's say we had a vector coming up like this, and then we added another vector to it coming like this. The resultant vector would be from the start of the first vector to the tip of the last vector. So this would be our resultant vector right here. And so when we want to find our resultant vector, we can just add up both of the x components of these two and the y components of these two. So if we call this like v1 and v2, we can get the x component of 1, the x component of 2, the y component of 1, and the y component of 2. And we now just made the components of this resultant vector. So if I draw this without all this stuff around it, we'll have the resultant vector here, and the x component and the y component. That's very wiggly. And the y component here. And this just equals the v1x plus the v2x, and this is just the v1y plus the v2y. And that's how we can solve for our resultant vector using those equations before. So let's do a couple adding examples. Alright, so the first example here, we have these two vectors and we need to add them. So what we can do is start by drawing the first vector. So we see that we'll do these graphically first and then also show how we can do it algebraically. So we see that it goes up 1 and over to the right 3. And then the second vector goes up 2 and over 2. Like this. So after drawing those two vectors, all we have to do is find the start from 1 to the end of the last one. And then now we've just made our new segment. So we have this segment of 3 and this segment of 2. This is 1 and this is 2. So now we found our components, and we can go ahead and find the magnitude of this resulting vector using the formula from before, where v equals, and I'll just use v for vector in this case. So if we wanted to find our vector in the x direction, it'll just be this 3 plus 2, and then our velocity in the y direction is just 1 plus 2, and we can plug these in and get 5 squared plus 3 squared, and that'll equal 5.83. That's our magnitude of this resultant velocity vector, or vector. Alright, so let's do another example. So now we have them moving in a bunch of different directions. So we'll follow the same steps. So we'll give the start point like right here. And so we first have just a 2 unit vector right here. And then it goes up 1 and over 4 to the right. So we can draw that in. And then it goes down 3 and over 2. So it'll go down to here, right? Okay, so our resultant vector will then just be the start to the finish. Like this here. So this is our resultant vector. So now, if we're doing this on like a graph paper here, we could just count the blocks from this resultant vector, and that's it. And we would have it down 2 and over 1, 2, 3, and 4. And we could calculate the magnitude this way. And we can simply get this, resultant vector as the square root of 2 squared plus 4 squared. But we could also add up each component as we've done before. So we could find this Rx, which will be 2 to the left, so we'll denote as -2, plus 4 to the right, and then another 2 to the right. And we would get 4 for our x direction. And then if we wanted to find the y, we see that this is first 0. This first vector doesn't move at all in the y. And then the second vector moves up 1, and the last one goes down 3. And that's a -2. And so if I plug these in, you'll get the same values, because since this is squared and we're just worried about the magnitude, the direction won't affect anything. So if we rewrite our equation with 4 squared plus a -2 squared, you'll end up getting the same answer. And it'll come out to be around 4.47. These are the 3 kinematics equations we used before. And every time we do a problem, we'll have to break up the problem into its x direction and its y direction. So these are just the same equations, but as we talked about before, when we're on Earth in free fall, the gravity will replace the acceleration, and everywhere there's x, it'll just be y. So you can't do a problem where you're not in the same plane of motion, and usually, in most cases, it'll be easiest to break up into x and y so that you can solve for different variables. So we'll do an example and how to kind of go about working through problems. So we have Bob kicks a football with an initial velocity of 20 meters per second at an angle of 30 degrees from the ground. The football lands in the stands 5 meters higher than the field. Determine how far horizontally the ball traveled, assuming air resistance is negligible. Okay, so first off, let's just write what we have. So we have our velocity initial is equal to 20 meters per second. We have some angle that's 30 degrees, and we have this 5 meters higher from the field. So what is this value going to represent, this 5 meters higher? Well, I think it'll be easiest to understand if we just draw a little picture. So we'll say this is the ground level, and the ball is initially kicked at 20 meters per second at this angle right here. This is theta. And I'll keep this all actually in symbols here. So this will be the v naught. And so this ball is going to travel up and then come down and land at this final position, which is 5 meters higher right here. So this is going to be from the starting position at ground level 0 to 5 is this change in y. So this change in y is going to be equal to 5 meters. Alright, so we have these little bits of information. We need to figure out the change in x, how far it traveled horizontally. So this distance right here will be the change in x. So how are we going to figure this out first off? So let's figure out what we have for each direction and then what equations we can use. So let's start in the x direction. Right, so we know the velocity initial and we know the angle, but we need to break this up into its components of Vx and Vy for the initial. So if you don't know how to do this, I made a video about breaking up components, so I would recommend watching that. But we learned that using some basic trig that the velocity in the x direction is just going to equal the v naught cosine of the angle. And so when we're working in this x direction, we see that there's no air resistance. So that means that there's going to be nothing in the x direction accelerating this ball. So the acceleration will equal 0. And so since acceleration equals 0, if we know that acceleration, I'll just write over here, equals the change in velocity over time, if the acceleration is equal to 0, the change in velocity also has to be 0. So this initial velocity will also equal the final velocity in the x direction. And so we want to solve for this change in x is what we're looking for. And so we need to figure out what equations we can use, right? So there's nothing that just has these variables in it that we can immediately solve for the change in x. But one that can get us pretty close would be this x final equals x initial plus vx naught t. And so we don't have this t, but we can move this over to get change in x is x final minus x initial just equals the change in x. And then vx naught, we already found what this equals is v naught cosine of theta times t. So we don't know t, so we're kind of stuck right now. We can't do anything further in the x direction. So let's look at the y direction and see what we have. So in this y direction, we, again, in the same way, we can find the initial y by just doing the initial velocity sine of theta. And so that will give us our sine of theta. But in this case, we cannot say that this equals the velocity final because there will be some acceleration in the y direction, and we know that's just gravity, which is 9.8 meters per second squared. And also note that the gravity is acting everywhere, and it's always going to be pointing downwards. So this will be we'll denote this as a negative sign here. And then we also know, as noted before, the change in y is equal to 5 meters. So we need to figure out what equation can we use to solve this, right? So most likely we're going to try to find time because we need this change in x, we know these two, but we don't know time. So what can we use to solve for time? So if we go up here to see what equations we have, this one we could use to solve for time, but we don't have the velocity final. This one we could solve for time, but this one doesn't have time at all. So we have a few options. We could either just use this equation and use the quadratic formula, or we could solve for the final velocity using this equation first and then go back and find time using this equation. And that's actually what I'm going to choose to do. And you'll see why in a moment how picking your right signs and on your quadratic formula can get a little bit more confusing. I think this way is a little bit more intuitive. So I'll start by using that equation. So we have this velocity final in the y direction squared equals the velocity initial in the y direction squared plus 2g delta y. And so we want to solve for the final velocity. So we can say that the velocity, leave some space here, we can say that the velocity final y is equal to the square root of v naught y squared plus 2g delta y. And so this is what we get for our velocity final. And we could plug in numbers here and get a value. But we could also just plug this back into our second equation. And something important here is we want to find this final velocity, but this could also be plus or minus. This could be like a plus or minus here. So which one do we want to use? And if we think about it, there's going to be 2 points where this velocity final is at this change in y, and it'll be right here and at right here. So when it's right here, the velocity in the y direction is still going up, but at right here, the velocity in the y direction is going down. So that's why it's important that we use a negative right here on the square root. So I'm going to scroll down to give a little more space. So now we have this velocity final, and so we also have this equation that we can plug this back into, a velocity final in the y equals velocity y initial plus the gravity times time. And so now if we plug this whole part into here, we get negative square root of v naught y squared plus 2g delta y equals vy naught, which we also know what this is. And I'll probably solve for this before just because it's going to get a little messy if we plug in a bunch of variables there. Plus gt. And so now we just need to solve for the time here. So if we subtract this over and divide by g, we can get time equal to this negative vy naught minus the square root of vy naught squared plus 2g delta y divided by gravity. We can solve for our t. So we can go ahead and plug in the numbers now. Of t is equal to this negative, and then we have to break this up into its components, so we can do the velocity initial, which is just 20, sine of theta, which is 30, minus the square root of this entire 20 sine of 30 squared plus 2, and this will be a negative 9.8, and change in y, which is 5. And that's positive because it's going up 5 meters. And then all divided by a negative 9.8. And so when all of this is worked out, we get a time equal to about 1.64 seconds. And now we can go back to the x direction and plug this in and see that when we plug this in, we get the change in x is equal to the 20 cosine of 30 times this 1.64, and that'll give us our change in x equal to 20.2 meters. Okay, so a lot of work for this little problem. The biggest thing here is break up your directions, see what equations you can use, and see what relates the two directions. And most times it'll be time, and we know that time is equal because when the time is going from one place to another, it doesn't matter what direction the time is, it's always going to be the same time. So usually time is what connects the two directions. So if you're trying to connect them, try solving for time in one direction and then using that to solve for your actual unknown. Alright, so let's do part B down here, which says, what is the max height of the football and at what time does it reach the max height? Alright, so let's think about what we have here. So we know we still have the same initial velocities that we had before. So we still know, like, in the x direction, we have our velocity initial x is equal to the 20 cosine of 30, and we still know the x direction acceleration is equal to 0. So this is still going to be the x final in the x direction, which in this case is at the max height. But in the y direction, we have this y initial, or this velocity initial in the y, equal to 20 sine of 30. But what is this velocity final in the y direction? So if we think about this, when the football is at the max height here, the acceleration is pulling down on it. It's going up, 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 up until it reaches the max, and then it starts coming back down. So at this instant of the max height, there is no velocity going up or down for that split second. So we can say that the velocity final is equal to 0. And then we still have gravity, which is a negative 9.8. And we're trying to find what is this max height. So what is the change in y here is the question. So if we go back to our equations, we have v initial, v final, and gravity. So if we look back at our equations, this has v initial, v final, and gravity, and all we need is the change in y. So we can just use just that equation to solve this. So if we have v y final squared equals v y initial squared plus 2g delta y, we can rearrange this by subtracting to this side and dividing by 2g, so that our change in y is the v y final squared minus the v y initial squared divided by this 2g. And so if we go ahead and plug in all of our values, we can get the final as 0 squared, I guess, minus the initial, which is the 20 sine of 30 squared, all over 2 times a negative 9.8. And this will get a change in y of about 5.102 meters. And so, okay, so then what is the time? So we can go back and see, now that we have all this information, we see that this first equation is pretty simple. We have final, we have initial, we have gravity. We can easily solve for time there. And so if we use the VYF equals VY naught plus GT, we can rearrange this as time equals the VY final minus VY initial over gravity, which is just going to be 0 minus this 20 sine of 30 over a negative 9.8, which will give us a time equal to 1.02 seconds. And notice here that this time is not just half of this. And if we had a situation where the ball started and ended at the same time, then this time might be, well, it would be half at the peak of its height. But since it's landing somewhere higher, it's being cut off short, so that this time can't just be half. So you'll have to be careful and actually solve for the time in this case. Alright, that's all of AP Physics Unit 1. If you watch straight through, congratulations. You're pretty locked in on physics. Stay tuned for Unit 2, and thanks for watching.